All right, well, welcome to BC Intertopics. We're going to review polar graphs. And when you were in pre-calculus, it's been a while, but you did do polar graphs. You probably went through and learned how to do them without a calculator, but then maybe started relying upon the calculator as time went on to graph these. And in BC, you typically will not be allowed to use a calculator, yet are going to have to be able to graph with a fair amount of accuracy polar graphs. And so I want to go through the basic forms with you. There's also a link up here to a really nice video that I think explains things really well and maybe in a slightly different way than I will. So I think could round out your knowledge really nicely. So the first type is circles. The way you would identify an equation of a circle is it would be r equals some constant a. A is actually going to end up being the diameter of your circle. And a can be positive or negative, and then it's going to multiply either sine or cosine. Keep in mind from back when you did the unit circle that cosine was an x-coordinate, sine was a y-coordinate. That can help you as you're drawing these circles. If it has cosine, what's going to happen is your diameter is going to be the x-axis, will be lying upon the x-axis. If a is positive, your diameter will be on the positive side of the x-axis. If a is negative, your diameter will be on the negative side of the x-axis. And sine is along the y-axis, a positive diameter for a positive value of a, and then along the negative side of the y-axis here. All right, and that might be a little bit of a false way to even say some of this because we're really kind of now talking about r instead of x and y, but that's a way to kind of maybe link some ideas together. Okay. So let's do a few, and I'm going to show you also a strategy that I think is useful if you forget what the pattern is. So r is equal to 4 times the cosine of theta. 4 is the diameter. And since this is along cosine, or since this is a cosine function, we're going to be along the x-axis. It's a positive 4, so I'm going to go 1, 2, 3, 4, and I'll be drawing a circle to the best of my ability, which is maybe not so great, but I'll do my best with a diameter of 4. Okay, you really should be a little more symmetrical there on the x-axis. Let's say, though, that you forget. You're like, I don't remember what's what. So you could pick some values of theta and substitute them into r. You can pick some rather easy values of theta, like the quadrangles. You're going to see some values repeat here, but this would help you remember. If you can remember, oh, this is a circle, this will reinforce it. If theta is 0, 4 times 1 would be 4. If theta is pi over 2, 4 times 0 would be 0. If theta is pi, cosine of pi is negative 1. This will be negative 4, but in the direction of pi. 3 pi over 2, cosine of 3 pi over 2 is 0. Times 4 is still 0. And then 2 pi, cosine of 2 pi is 1. And so times that multiplier 4 is 4. I'm just going to plot these points. In the direction of a 0 angle, we're going to go 4 units. In the direction of pi over 2, we will move 0 units. In the direction of pi is this way, we would go negative 4. That pops you back over here. In the direction of 3 pi over 2, we're going 0. In the direction of 2 pi, we're going 4. Now what happens is we've got to get from 4 to 0, and so we end up circling around. You could also pick some values in here like pi over 6, pi over 3, pi over 4, and plug those in as well in order to get some answers. My circles are awesome. It is right now 5 in the morning, so that's as good as it's going to get. If you have a circle and the equation is something like y is equal to negative 3 sine of theta. This is sine, so it's going to be along the y-axis here in terms of where its diameter is. And since a is negative 3, we're going to be along the y side of the y-axis, and our diameter is negative 3. 1, 2, 3. Not a better circle. I was hoping it'd be a better circle, but a little bit of a fail. And looking at this one, if you did need to, you could go back and plot some numbers. The sine of 0 is 0. The sine of pi over 2 is 1. And so times negative 3. Sine of pi is 0. Sine of 3 pi over 2 is 1 times negative, or sorry, is negative 1 times negative 3 would now make this a positive 3. And then sine of 2 pi is 0. So if I plotted some points here, 0, 0. In the direction of negative, or in the angle of negative 2, we are going in the direction of negative 3, which pops us over to the other side, right there. At pi, we have 0. 3 pi over 2, we want to go to 3. 2 pi, we're going back to 0. And there it is. Cardioids are heart-shaped graphs. A couple things that you should know about a cardioid. When you're looking at the equation of a cardioid, you're going to have two numbers. So you're going to have kind of similar, like this was kind of like what a circle looked like, but you have this other number in front of it. And then you have either a plus or a minus in between. So some things about cardioids, these need to be the same value. A and B need to be the same value. Now you can have a plus or minus between them, but they need to be the same in order to have this shape. We'll talk about why when we plot some points. If you see cosine, it's symmetrical to the x-axis, and the x-axis is it's kind of going right through the heart. And if it's a sine function, it's going through the y-axis, or symmetrical through the y-axis. If there's a plus sign between them, we're going to be primarily on the right side here. A minus will shift it to the left. A plus with sign will go above. Primarily, you're going to see it dips below, and it'll go down to the bottom. Now, this is helpful too with the cardioid. That little dip of the heart is going to be on the origin. You're going to see that on every single one of the cardioids. And I think that it's helpful on the cardioids to maybe plot a few by using values of theta and figuring out then what R would be, so you can see where the pattern exists. So for the first one, I'll do R is equal to 2 plus 2 sine of theta. 2 plus 2 sine of theta. Notice that A and B are the same values. Same values. Now, because it's sine, it's going to be along the y-axis, symmetrical along the y-axis. And because there's a plus here, I'm thinking it's going to be primarily up on the top part, with dipping a little bit beneath. But let's just plug some angles in here. I'll do the quadrangles and see what happens. If you know the generalized shape, you can at least recognize the general shape, you can always plug in some values of theta to help get a little bit more of an accurate graph. Without knowing the generalized shape, you would have to really plot a lot of points. So like I'm only plotting the quadrangles, but if you really didn't know the generalized shape, you should also plot significantly more points, probably like pi over 4, pi over 6, pi over 3, until you get a really good sense of what's happening. Well, the sine of 0 is 0, so this part zeroes out and we get a 2. So in the direction of a 0-degree angle, we'll move 2 units. That then is not going to be helpful. There we go. Let me change the font. At pi over 2, sine of pi over 2 is 1. Times 2 is 2. Plus 2 more is 4. So in the direction of pi over 2, we will go 4. At pi, I have a sine of 0. Adding to 2. And at 3 pi over 2, I get a sine of negative, our sine of 3 pi over 2 is negative 1, times 2 is negative 2, plus 2 more zeros out. This is why we go through the origin on these cardioids. And then at 2 pi should mirror 2, which you probably don't have to do. But the way I want you to think about this is what's happening here is you are, as you move through this, as it connects. Because we know this is a cardioid, you know it's going to have that heart shape and it's going to dip into the other side here. That's what's happening over here. If you really wanted to see like more specifically how it dipped, you could plot some more points, but this will be sufficient. So why don't you pause the video and try to graph this one. Y is equal to 3 minus 3 cosine of theta. Pause the video, try it, and then we'll compare. All right, so I'm going to recognize that this is a cardioid since A and B are the same value. Because this is a cosine function, this is going to be symmetrical around the x-axis, and since this is a minus, it's going to primarily be on the left side. So I'm thinking it's going to, kind of go around this way. Now, as I graph this, a pattern that I want you to see, because you do really actually want to know how far does this go. I'm not going to do 2 pi because it just repeats. But you could, if you wanted to, just repeat 0. I'm going to plot a point or two. If I plug in a 0, cosine of 0 is 0. So that zeroes out times 3. So 3 minus 0. And then if I plug in pi over 2, at pi over 2, I'm going to get, oh, sorry, that doesn't zero out. I'm losing my mind. Cosine of 0 is 1. 3 minus 3 is 0. Sorry, I apologize. Pi over 2, cosine of 0, or cosine of pi over 2 is 0. 3 minus 0 is 3. At pi, the cosine of pi is negative 1 times negative 3 makes it positive 3. Plus 3 more is 6. So this is something I want you to see. When you're graphing these, and you could have seen it over here, basically you take the A and B values, and regardless of the sign, if you combine them together, the absolute value of A, don't worry about the negative here, just A, 3 plus 3 is 6. That's how far we go into the graph for the end of the cardioid. 1, 2, 3, 4, 5, of course, 6. And we're going to have these multiple points right here along this axis because at pi over 2, we're going to go 3. This is how we'll get that heart shape. 3 pi over 2 would also give me a 3 because it's going to zero out for the cosine part of that. And so here's basically what's happening. It loops around. I find it easiest to graph if I start at that dip of the heart for the cardioid. Something like that. It's probably actually a little bit taller on each edge. Sometimes I tend to make mine a little skinnier than they actually are. That's fine though, this would serve our purposes. Okay. So this word right here, there's, my gosh, there's so many different ways that people say this word. Some say limason, some say limason, some say limason, limacone, limason, or limason, limacone. I mean, it's just absolutely crazy. You'll hear me most of the time say limason, like the word limit, and then son. Sometimes I say limason, or even limason. It's kind of just based on my math background. Different teachers and professors have said it differently, and so it's stuck in my head in different ways. So I might say it differently than your teacher last year, for example. I think Earl says limason. I think I tend to say limason or limason the most, but we'll see how it goes today. All sorts of interesting things might be said at 5 in the morning. Okay, pen work. Yes. Okay. A limason with a dimple actually has a very similar generalized format to our cardioids. But the difference is what's happening with A and B. What's happening with A and B. So A must be larger than B. These are not going to be the same. And what's going to happen is it's going to, you might remember that when A and B are the same, we would get this spot where we would zero out. And that's why our heart of the cardioid, or the little dip of the cardioid, would go right to the origin. Well, what's going to happen with a limason,